Okay, let's talk about kinematics. We introduced this idea of instantaneous velocity last day, where the delta t in our operational definition had to be small. Small enough that we didn't have time to speed up or slow down. Small enough that the motion during that interval of time looked uniform. Was a straight line position versus time graph. Now, when we have a graph like that, we recognize that it's not uniform. Now, we have a wonderful lab activity where you actually move your body in front of motion detectors, and it helps you figure out how to draw these graphs. It's really a good experience. Unfortunately, we only have enough setups for the engineers, so we lose. So what we're going to do is we're going to do a cheap version of that activity. We're going to let me be the object that moves, and we're going to move on a coordinate system that goes positive towards the open door, negative the other way, and that will be the origin of our number line. So if I want to make that graph, that velocity, position versus time graph, where should I start? At the origin. Which way should I go? Towards the open door? Towards the open door. Should I start fast or slow? Slow. I start with zero velocity, and then I slowly take off, and then get faster and faster as I go. Fat man running. Okay? Now, what we learned last day was that if we wanted a velocity versus time graph, what we needed to do was collect data points. We go in at different times. This will be noon. This will be 1 second afternoon, 2 seconds afternoon, 3 seconds afternoon. So at noon, I would draw a tangent line. I would take any 2 points on that tangent line and compute the slope. I can eyeball that. It's got a slope of 0, okay? And so I would put a data point there. At time noon, I have a velocity of 0. I then do that for 1 second after noon. I find the slope of that tangent to be 2 meters per second every second, okay? And I put that there. I'm sorry, I misspoke. I found it to be 2 meters per second. Full stop, period. I do that at 2 seconds, and the slope of that line is 4 meters per second. I keep doing that and collecting data points. At some point I get bored and I just connect the dots. Now that graph is a straight line. Whenever I have a straight line graph, I want to interpret the slope. What interpretation can you give this slope? What does that slope tell you about this object?
Acceleration.
It's the acceleration, that's the name. But what interpretation can you give this? It turns out that the slope is 2. What does 2 tell you about the motion of this object? Yes, sir?
It's accelerating at a uniform rate.
Okay, it's got a constant acceleration. And what does 2 tell me about that motion?
It's accelerating at 2 meters per second every second.
Okay, and where would I see that? If this was a car that was doing that, where would I look to see that happen?
Speedometer.
On the speedometer, yeah. What would happen is I'd look down at the speedometer. If I happen to have one of those fancy cars that read in meters per second instead of miles per hour, it would be increasing by 2 meters per second every second that ticks by. Okay? Now if I take the slope, I take the rise over the run, and I would get 2 meters per second per second. Now I would like you, please, to pronounce it this way. 2 meters per second for each second, indicating that this second is part of the change in velocity that happens on your speedometer, and it happens in a unit of time, 1 second. Okay? Good, thank you very much. So this is my operational definition of acceleration. You used it during tutorial this week. And remember, it's important that we always take 2 data points to calculate our change. Always 2. You remember the analogy with the weather. If you want to know what the weather is, stick your head out the window. If you want to know how it's changing, you got to stick your head out, pull it in, wait 5 minutes, stick it out a second time. Okay. Now, in this class, we are going to concentrate on problems where the acceleration is constant. By that I mean that the velocity versus time graph is typically going to be a straight line. Now, that's not always going to be true, but primarily. And that's because there's enough richness, there's enough mess with these types of problems. We don't need to go looking for more mess. Now, you'll notice for constant acceleration, the distance traveled in equal intervals of time is not the same. However, the change that happens on the speedometer would be the same. In every 4-second interval of time, we change our velocity by 20 centimeters per second there. Okay, simple problem. A car is moving 50 miles per hour east. 10 seconds later, it is moving at 70 miles per hour east. Find the car's acceleration, magnitude, and direction with your neighbor. Would you please solve that? Okay, let's do it together now. The final velocity is 70 miles per hour east. The initial velocity is 50 miles per hour east. That change happens in a time of 10 seconds. That's going to be a change of 20 miles per hour east in a time of 10 seconds. And that's going to give me a final answer of 2 miles per hour for each second east. Okay, magnitude. The magnitude is this number. That's always going to be a positive quantity. And the direction is east. Okay, let's try another one. A bear is running at 4 meters per second north. The acceleration of the bear is 3 meters per second squared. Now, meter per second squared is a legitimate unit for acceleration. It's what's used in most textbooks. But sometimes trying to visualize a square second is tough. So I'm going to try, whenever possible, to write that as 3 meters per second for each second. The question is, what's the bear's velocity 2 seconds later? So really quick with your neighbor. What's the bear's velocity 2 seconds later? Okay, what's the answer? Shout it out. 10. Okay. The acceleration is the same direction as the initial velocity. That means every second that ticks by, we're adding a change vector in the same direction as the velocity vector. That's going to make my velocity vector longer and longer. This bear is speeding up. If this bear had a speedometer in his belly, it would start out with a reading of 4 meters per second. Every second that ticked by, that speedometer would move up by 3 meters per second. So it would start at 4. After 1 second, it would be at 7. After 2 seconds, it would be at 10. It's that simple.